Hey everyone. Okay, this is our lecture on the introduction to the scientific method. This is intended to be followed by the introduction to science. I hate to give away the game here, but I do expect and will ask on tests for my students to be able to reason through these topics, to communicate them using the proper definitions, and to apply the knowledge. So you can see on the slide here a picture of just a representation of the scientific method. And this one works as well as many of the others, although if you Google it, you can find other pictures of what it looks like. And I'll give you some background here. We went to a meet the teacher date last year for one of my kids, and we walked into their classroom. It was a fourth grade classroom, and they had a big poster about the scientific method on the wall. And so I had this aha moment that my college-age students have been seeing this for years, and why am I still lecturing on this? Well, whatever it is that they communicated in grade school and high school and beyond, I don't know, it appears to not have stuck very well. So I think it's still worth it to try and cement some proper ideas. Not that, it's okay to have different ideas about, a hypothesis and a theory. But let's try and give you a more formal definition and help you to use it in the way that's kind of intended in science. So you have a picture here, right? You have kind of an iterative process over here, right? The whole thing is iterative, but the iterative process here is kind of like doing experiments. So you come up with some hypothesis, which gives you a prediction for an experiment. It has to be testable. And then you do an experiment, you get the observation, and then maybe you need to refine it or refine the experiment, and you repeat this process. And this results in a body of knowledge that can be used to either generate a law or a theory. So if you look at this picture, there's something interesting. There's no line connecting these two. There is no line connecting law and theory. All right, they're two independent things. And sometimes you have a theory that explains a law. We'll give an example of that today in atomic theory. And then sometimes you don't. All right, sometimes a law just stands alone with no theory. There's not any rule about one preceding the other. Okay, so this kind of summarizes everything, but there's still a lot to learn about what's actually going on here. And to illustrate this principle here, I came up with what I call a preview poll. And the first question on our preview poll, and you guys just think about this on your own, and see what you would put. Rate the statement as never true, rarely true, sometimes, or always. Right? So 1 through 4. A scientific law is called a law because it can never be broken. Okay, would you say that's always true, sometimes true, rarely true, or never true? Right? And I think most of my students, and this is an okay kind of initial interpretation, I think most of my students would say that's always true. It's a law because it's a law. And I want to kind of add some nuance to this idea of a law, like as if it's a law that was passed by a judge or something, and you can't ever break that. All right, sorry, it's passed by the legislature, enforced by the judge or something like that. A law is, in science, is based on observations, and we can have new observations that refine our ideas. And so going back to this thing, right, this whole process is iterative. We keep refining our knowledge and laws and theories in a continual process. So yeah, sometimes a law could be broken. There's lots of examples we could go through on that. What about this one? Read the statement. Is it never true, rarely, sometimes, or always true? 1 through 4. A scientific theory is just an idea, and it may be true or not. So I'll contrast this with the previous question, right? The view that people have is law, set, always true. Theory, maybe, maybe not. And this is just not really the case, right? Theories are just as set as laws. Yes, it is true that laws can sometimes, we can sometimes refine them and change them. Same with theories, but theories are just as solid as laws. But there's a difference between what laws and theories are doing. And so we'll get into that in a little bit. So I'm hoping that by this preview poll, I'm sort of shocking you a little bit. And this next one, maybe I crossed the line about this one with this one, right? Same thing, never, rarely, sometimes, or always true. We must always accept what scientists tell us about the world. So yeah, maybe I crossed the line on that one. Would you say never, rarely, sometimes, or always, right? Scientists are people, right? We're making interpretations on data, and sometimes scientists can be wrong, right? Sometimes science can be wrong. And most of the times, there's a lot of theories and laws, which we know pretty well, all right? But then when we get on other, sort of complex topics, not so much the case always. All right, and then the last one, a scientific study must be true. Never, rarely, sometimes, or always true. Well, um, this last one, it's like really puts me over the top, and students are, calling me out on this in class, right? We have fun with it. But a scientific study must be true. This is, I'll give the example of advertising again. There are lots of scientific studies that need a lot of help, all right? And so you got to be careful with with what we do with scientific studies. Okay, all right. So that's just a preview. Let's go ahead and get into some of the actual definitions. Right, the scientific method is a general procedure, right? A general outline for how things should be done. It's loosely called the scientific method, although there's not really one universal method. When scientists go in for each work each day, they're not like, I'm here to do the scientific method, right? So it's kind of implied for them. But overall, we're going to learn this process. It's a good thing to learn and to know about, and it's a good process. All right. So the characteristics of scientific inquiry: it's observations based. It generates predictions. These predictions need to be testable and falsifiable as a very critical test. And then it requires communication, and then replication and validation. So we do this through scientific journals these days. We publish it, and then other people can challenge it. They can put comments to it. They can run their own experiments. So they should be able to validate or replicate that experiment. And then the whole process is, I think this word's made up, reiterative. So we have to just keep going through this process over and over again. Okay, observations are the process of using a series of experiments to gather information. We use our senses to get this information. We have instruments sometimes to help us, accentuate our senses. And then a lot of times we want these to be quantitative, but sometimes they can be qualitative, right? So qualitative and like a yes or a no, or like color or something like that. And then these observations are organized to try and find a pattern. All right, we're looking for those patterns in what we see a lot of times. All right, so when we find that pattern, then we want to explain it. All right, why would this be the case? In a nutshell, that is science. Like, why is this happening? And then we use those patterns in our explanations to try and develop, another test. Right, test our ideas. And then we just continue testing our ideas over and over again. All right, so a hypothesis is a very important distinction here. It's a falsifiable prediction, all right? And we need this to be testable, right? I already mentioned falsifiable, and usually to design an experiment. All right, and you can kind of think, hypothesis comes, you do some testing, and it's okay to kind of think of, first you have hypothesis, then you have theory or a law. People kind of put hypothesis as at the testing stage, and then a theory is an explanation that we kind of are set on. And then we may get a law out of something, right? You can usually phrase this as, if one does this, then we expect to see X happen, all right? An experiment is just kind of what you would expect. It's a controlled observation. We try and control as many of the variables as possible so we can isolate just one variable at a time. That's what we typically try and do in an experiment. Factors are arranged so that we can infer cause and effect. All right, so we try and eliminate a lot of external variables so that we can see cause and effect very clearly. Okay, you guys get the idea? There's some definitions that you need to know, some ideas and concepts that you need to know, just in order to discuss this, right? We might do observations or field work, another sort of doing experiments. So it doesn't always take place in a lab with people wearing a white coat and such. And then we communicate all that stuff to others. Very important part of the process. So this is a built-in set of checks and balances, right? People make mistakes. And the way we get around that is by communicating, and then everybody else tries to check it. Okay, so just a repeat here of the previous slide: observations, we generate predictions, and then we communicate and we repeat that process. Okay, this process has been going on for a long time, and this cycle just keeps expanding our knowledge and hopefully refining our ideas and making them better and better. And I think we can say that it's been pretty successful. All right. As we test ideas through experiments, then it gains, the ones that make it through gain credibility. All right. And we can increase our confidence in those ideas, those theories, and those laws. Okay. All right. Very important. You need to get these two terms down. And, I have a simple one-word definition for each of them. All right. A law. When you see law, I want you to think a summary. All right. It's a generalized statement which is summarizing a bunch of data. It's often mathematical, right? So it's not going to seem as a verbal summary sometimes because it'll be a formula, but it's just a summary. Think summary. So we have a lot of tested and validated observations on something by the time we get to a law usually. And then my one word for theory is it's an explanation. Okay, if you want that to be your starting point, it's a great place to start. Laws, a summary, theories, an explanation. You should hopefully expand beyond that, but that's a great starting point for understanding these topics, which are really important in the scientific method. So here's just a quick example, right? A law summarizes. An example would be gravity, right? It's the law of gravity. It has a formula that goes with it, right? So this formula is a summary of repeated observations of things fall, right? And more generally speaking, things are attracted to each other through the law of gravity, as explained by this formula here, all right? Whereas a theory explains. In this case, we didn't have a theory for the law of gravity until general relativity a couple hundred years later. That was when Einstein came up with this idea of you're actually distorting space-time. We don't need to get into that. That's more physics. But a theory explains. In this case, you have a theory explaining the law of gravity. Okay? All right, so in order to illustrate this, I thought we would illustrate all of the ideas of the scientific method by looking at a very important development. It's where they typically start with chemistry anyway, so it's kind of killing a couple of birds with one stone, and that is atomic theory. So when you guys think about the atom, you probably have an idea in your head, but it's important for you to know that we've never actually seen an atom the way that you think in your head typically. All right, this is about the best we can do. This is an instrument that pictures atoms as just sort of lumps on a surface. It almost looks like a bent metallic plate in there with these lumps for atoms. And this is about the best we can do, even to this day. So if you think about that, how did they even come to the idea of atoms if we still can't even picture them? All right, so they had to infer this from a series of laws, and in this case, they came up with a theory to explain those laws. But they had to make intuitive leaps in order to generate this idea. And we'll see that there was some beginnings of the idea a long time ago, but it took a lot of work to get there. All right. So when you guys think about an atom, first think about my little general explanation here. First, think about a pie, right? If you had this pumpkin pie here, it just all looks like one type of substance in here. And a long, long time ago, some guys were sitting around thinking about this, and they said, hey, if you cut this pie in half, you have half a pie. All right, then you cut it in half again, and you have a quarter of a pie, and you just continue that process, cutting, 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 cutting. They postulated that eventually you would get to a point where you couldn't cut it anymore, and they called this indivisible, right? The word that they came up for it was that in Greek. These were a bunch of Greek guys, and this was the kind of the start of atomic theory. All right, they really didn't have an experiment. This was all just kind of a thought experiment for them, and it was by a guy named Democritus, and Leucippus, I forget which one actually came up with it. 5th century BC. All right, long, long time ago. And it's kind of like a general comment on the Greeks, right? We sort of trace Western thought back to them, and it's true if you read the original writings. It's very impressive what they were doing. There were lots of other people around the world who were doing this, though. And just something about the Greeks, they really didn't like to do experiments, right, to get their hands dirty. They more just preferred to think about things, which is why they tended to focus on math a lot more. But he had an idea here, and these two guys, Leucippus and Democritus, that things were eventually indivisible. Well, you've probably never heard of these guys, but you probably have heard of Aristotle. And Aristotle didn't like this idea. So in an argument between this forceful person of Aristotle and then Leucippus and Democritus, right, who do you think won? All right. So I try to make this into a story for you guys, and if you'll just take it with a grain of salt, right, it'll help illustrate this. And I have tended in the past to make Aristotle the villain, all right? But, again, it's just trying to make it into a story and make it more interesting. But this idea that Aristotle had was that everything was made of four elements, right? And so it wasn't that things were eventually indivisible. They were made of these four elements, and everything was just a different combination of these four elements. So this idea of things being made of four elements, although discredited in a way, still lives on even in pop culture. So if you have seen the Last Airbender, right? I think that's the name of the show. They deal with this idea. There's lots of other pop culture things that have this. The four main elements were earth, air, fire, and water. And the way they explained everything was just this different combination, right? So you've had something like, a plastic piece on your phone, something like that. It's just a different makeup of, mostly earth, and then you mix in some fire and some water and a little bit of air, and just different percentages making up that, versus something like wood, which is a little bit of a different substance, right? So maybe it has a little bit more earth and a little bit less air, something like that. You could see that we could make a compelling case for everything being made of this if you just think about it for a little bit. And imagine everybody that you knew that was smart told you this was the case, right? And I think it's also important to know, right? So then if everybody said that, you would probably just go along with it. But also it's important to note this was an attempt to explain things in a way. And so I think this is a very important development in science, even though we ultimately know it's not true. But the idea that everything was made of four elements was eventually replaced by the idea of everything being made of a bunch of different elements. So it's like kind of true, right? There's some development going on here. All right. So Democritus didn't actually disagree with this, right? So there's a little bit more wrinkles in here than just the simple story I'm trying to tell. But we got to move on a little bit. So Aristotle's reputation and this idea went on for a long, long time. Aristotle made a bunch of different developments. This was just one, right? Right. I'm making him the villain, but there was a lot of other things that he did. And there was also an idea that atoms and elements started mystical elements involved with them. So, the gods could change the elements at any time, right? So this sort of hindered science in a way. So we continue that for a long time, and we eventually have sort of the beginnings of modern science. People are starting to do experiments. People are starting to generate a body of data and knowledge. And one of these guys is Robert Boyle. This is around 1650, so 2,000 years later after these guys. And he wrote a very seminal book called The Skeptical Chemist. You can see that's not the whole title. And a lot of people think that the skeptical chemist meant that he was breaking away from alchemy, and it would be okay. It would be understandable even if you read the book to think that, because apparently the book was so confusing that even if you read it, you didn't quite understand what he was saying. But the skeptical chemist came to be the main title, so people thought he was being skeptical of alchemy. But a very important development, and also he kind of had this corpuscular theory of gases. So you can kind of see people are starting to identify little teeny tiny particles, right? That's what these corpuscles were. And the development would continue on until, right, he's credited, as one of the early guys doing the scientific method, and the process would eventually become known as the scientific method. But this process continued on until we had a couple of laws that people eventually figured out. So we're going to, what I normally do is set up this little versus, right, the four elements versus the scientific method. And let's see how this works out. Well, John Dalton was the guy who eventually put these pieces together, and he put them together to make a theory that explained three laws. So let's look real quickly at those three laws because we're going to go into them in a little more detail later, and just kind of see how he did this. The first one was the law of conservation of mass. So this law states that before and after a reaction, the mass stays the same. Now, this may seem totally obvious to you, right? But there are certain little technicalities that got people, right? So when you had a reaction, sometimes it would release stuff as a gas. They had to figure these things out. And so eventually they came up with it. And this was one sort of block that was going to be used as, the sort of intuitive stepping stones by Dalton to figure out atomic theory. The other one is an idea called the law of constant composition. And this just says, a compound is always going to have the same composition. They didn't know that this was the formula for water. They didn't know what was actually making it up. So it may seem obvious to us that H2O always has 2 hydrogens and 1 oxygen, but somebody had to figure that out, and they did. It's called the law of constant composition, and I want to spend even less time talking about multiple proportions. But these 3 laws were sort of developed, and Dalton made an intuitive leap, basically using these 3 laws to come up with the atomic theory. And the atomic theory was able to explain all 3 of these laws and the observations from them. So just to give you another idea, people think a law is better than a theory a lot of times, but in science, what scientists would rather come up with is a theory. It is viewed as superior. Why? Because it is an explanation. So this atomic theory explained that. And then, one thing I like for students to do is really think on your own, right? Do these 3 laws really disprove the idea of 4 elements? All right. Another thing, does the atomic theory actually explain them? How can you go through that? I'm going to go through these some examples of how to do that in some other slides, in some other lectures later on, but it's important for you to try and think through these things and think, can you actually convince yourself of this? So in summary, I hope you got out of this, right, the common idea that students have. A law is a fact, and a theory is a guess. No and no, to be technically true, to be technically honest here. All right, a law is always true, and a theory is sometimes true. No and no, all right? Based on our observations, we can say that a law is pretty much set, but there may be a new observation that comes along. And a theory is just as sure and set as a law, right? And in fact, theory is preferable to a law. Right? This is what we would rather find as a theory. So my homework to you, my encouragement to you is to start reading your text and get the basic ideas down. I do expect for you guys to be able to discuss these things, to discuss these laws and how the theory explains them, and to use this as an example to discuss the scientific method. So that's about it. Good luck, and have a good day.